Okay, welcome friends. In this class we will continue our previous class discussion which was on the free endpoint problem. In the previous class we have derived the Euler equation plus the terminal condition, and any free endpoint problem is we can define as in the different cases as per the variation of the delta xf and the delta tf, the different cases can arise. The two cases we have seen in the previous classes, one is the fixed endpoint problem in which both tf and the x of tf was fixed, initial point is also fixed, terminal point is also fixed. So, at terminal point delta xf and delta tf will be 0. The second case we have seen that in which tf is fixed and the xtf is free. So, in that case my tf point 0, so this whole will become 0, and in solving a problem first we will solve the Euler equation which will lead us to a differential equation whose solution will have the certain constants, and these constants we evaluate by using the initial point, initial condition as well as the terminal condition. In xtf free tf fixed point, my terminal condition was del v by del x dot by del x dot evaluated at t equal to tf point equal to 0. So, in this class we will start our discussion with the another case which will be our third case, in which we are making tf to be free and xtf is fixed. So, this is the case like means if this is my xf, this is the xt, this is t, and let us say this is my initial point t0, xt0 is say x0. So, my final trajectory can terminate anywhere with this where xtf is fixed. So, this means in this case also my tf is varying. So, as we have discussed in the previously also, once my xtf is fixed, so delta xf will be 0. If delta xf is 0, so in this case my this first term will become 0 and my terminal condition will be v dot, which we are evaluating at t equal to tf point minus del v by del x dot, again evaluated at t equal to tf point x dot tf delta tf equal to 0. As delta tf is free, so delta tf is arbitrary. So, we can simply write as v dot at t equal to tf point minus del v dot by del x dot, again evaluated at t equal to tf point x dot of tf, that must be equal to 0. In general, if we will write V XTF x dot Tf minus del V x of x dot of Tf by del x dot of Tf multiplied with x dot of Tf equal to 0. So, we have the two conditions now. One is if the one is the initial point is given. So, I am given with the T0 and xt0, xf is fixed specified. So, xf is given, Tf is free, which will lead to my terminal condition V minus del V by del x dot at Tf point multiplied with the x dot of Tf equal to 0. So, this we can use as my terminal condition. So, to explain it further, again let us consider example for this case, which will give us the more insight how to use these conditions to solve a problem. So, we take another example. Find an extremal for the functional this is 1 to Tf, means the initial time is given as the 1, two xt plus 1 by 2 x dot square t dt. So, our objective is to find the extremal of the functional Jx, which is subjected to the boundary condition. The boundary conditions are the initial point is given as x1 equal to 4 and x of Tf, because Tf is unspecified, this is also 4 and here my Tf is greater than 1. 1 is the initial point. So, Tf naturally will be greater than 1. So, this is my problem statement. We have to find out the extremal of the given functional Jx with boundary condition x1 equal to 4, xTf equal to 4. So, as the first step we have to solve the EL equation given by the first equation here. So, in this case my V is 2xt plus 1 by 2 x dot square of t. Euler equation is del V dot by del x minus d by dt of del V by del x dot, that must be equal to 0. So, with this value of the V, del V by del x is, from here I can simply write the 2 minus d by dt of dv by del x dot. So, this is nothing but giving you x dot equal to 0. So, my equation is x double dot t equal to 2. So, EL equation give me the another differential equation which is nothing but x double dot t equal to 2, and the solution of this. So, this gives me x t which is t square plus C1 t plus C2. So, if I will solve, so x dot is 2t, further I will integrate this to get the x star t as t square plus C1 t plus C2. So, this is the solution of my x double dot t equal to 2 which I am getting here. Now, I can use my initial conditions. I am given with the x1 equal to 4. So, x1 in this case is 1 plus C1 plus C2 which is equal to 4. So, my equation is C1 plus C2 equal to 3. So, by the initial condition we can find out one equation in C1 and C2 which is giving me C1 plus C2 equal to 3, and the second condition or say the another equation to find out the C1 C2 variable, we will get it from my terminal point. In this case TF is free, XF is 0. So, this term will be 0 and we are left only with this. So, what was my equation? So, my another boundary condition is V dot minus del V dot by del X dot x dot T f equal to 0. So, if I will use the V as 2 x t plus half x dot square t, I will get 2 x of T f plus 1 by 2 x dot square of T f minus. So, this is giving me the V at the T f point 2 x of T f plus half x dot square of T f, because my V is given me this value, minus if I will differentiate this with respect to x of T f. So, that is nothing but x dot of T f multiplied with x dot of T f, and this is equal to 0. So, I am simply getting as 2 x of T f minus 1 by 2 x dot square of T f, that is equal to 0. So, what we can get by this? So, I have x T f equal to 4. XTF is given to me as 4, and what was my XT? And if you will see, we have find the X star T as T square plus C1T plus C2. So, we can write this as, this is nothing but my TF square plus C1 TF plus C2. So, this is my XTF. And X dot TF, if I will write it from this is nothing but my 2TF plus C1. Now, I have my XTF as this, X dot of TF as this. I can place this value in this equation, 2x of TF minus 1 by 2 x dot of TF square equal to 0. So, if I will place it, so I have twice x of TF is TF square plus C1 TF plus C2 minus 1 by 2 x dot of TF is 2TF plus C1 square, and that must be equal to 0. So, if I will solve this, we get 2C2 minus 1 by 2 C1 square equal to 0. So, all other factors will be cancelled out, and this, if we will solve, we will get this value. So, I have the two equation in the C, one is 2C2 minus 1 by 2 C1 square equal to 0, and another is C1 plus C2 equal to 3. So, these two equations we have to solve to find the value of the C1 and C2. As we can see, my this equation is quadratic in nature. So, naturally I will get the two values for C1 and two values for C2. So, which value we will select, that will be decided by the condition which is given, what is the TF which is greater than 1. So, let us first see what the values we are getting for C1 and C2 in this case. So, this gives me C2 equal to 1 by 4 C1 square, placing this value of C2 in this equation, C1 plus C2. So, C1 plus C2, in place of C2 I write 1 by 4 C1 square, and this is equal to 3. So, this gives me equation C1 square plus 4 C1 minus 12 equal to 0, and this gives me the value of the C1 as, I have the two values of the C1, one is plus 2 and another is minus 6. So, I get the two value of the C1 by solving this equation, plus 2 and minus 6. Using the value of the C1, I can find out what is the value of the C2. So, C2 corresponding to 2, if C1 equal to 2, so C2 will be 1 with minus 6, C2 will be nothing but 9. So, I can take the value as 2 or 1 or 6 or 9. So, this means my optimal trajectory may be, so I have the two solutions, x star t as, if I will take the 2 and 1, this is t square plus 2t plus 1 with C1 C2 as 2 and 1, and the another solution is x star t as t square minus 60 plus 9 with the value of C1 C2 as minus 6 and 9. So, which is my solution? Which solution I will select for this? So, this we can select by finding the value of the TF. So, we can see from this equation, if I know the C1 C2 for the different value of the C1 C2, this will satisfy, let us say C1 equal to 2, C2 equal to what I am taking the C2, C2 is 1. So, these equations give me TF square plus 2t plus 1 equal to 4. This implies TF square plus 2t minus 3 equal to 0. If I will solve this give me TF equal to 1 and minus 3. For second solution, for C2 equal to, sorry, C1 equal to minus 6 and C2 equal to 9, I have TF square plus 2TF, naturally this is the TF, 2TF, sorry, I have to correct it. So, with C1 is 6, so this is minus 6 TF plus 9 equal to 4, or simply TF square minus 6 TF plus 5 equal to 0, and this gives me TF equal to 5 and 1. So, what was our condition? My TF should be greater than 1. So, in this case my TF is 1 and minus 3. So, this is not the solution. In this case my TF equal to 5. So, I can select the second equation So, this is the solution. So, in such a problem we have to find out what are my constants and simultaneously we can also find out what is my TF. So, in the solution my optimal trajectory here will be t square minus 6t plus 9 and the optimal time will be TF equal to 5. So, all the unknown parameter we can find out simply by solving using these two equations. So, in today's lecture we have taken the three cases in which we have the fixed endpoint problem. The second case was our TF was fixed and the XTF was free, and the third case was we have the XTF as fixed, TF was free. So, in the next class we will discuss about when both are free, then our these two equation will exist and the different cases arises in that particular case, that we will discuss in the next class. So, today we will stop here. Thank you very much for your attention.